homework solution 6.1. For the ideal transformer, calculate the unknown quantities in the following figure, as well as the power supplied by the source and the power delivered to the load. So we show that we've got an ideal transformer. There are really, on the primary side, three important parameters: the voltage across the primary coil, V sub P, the current flowing through the primary coil, I sub P, and the number of turns in the primary, NP. In the secondary side, we have four important quantities: the number of turns in the secondary, N sub S, the voltage across the secondary coil, V sub S, the current through the secondary coil, I sub S, and in this case we've just got a load resistance, so R. So we're given these parameters in A and B, and we're asked to determine the parameters that are not listed amongst these. So we'll just write those givens. It's written right here, but I'm going to say it out loud so you can all at least hear them. The primary voltage is 12 volts. The number of turns in the primary is 10. The number of turns in the secondary is 1, and the load resistance is 120 ohms. So that's the specifications given to us in A. And then in B, we have the primary current is equal to 0.01 amps. The number of turns in the secondary is equal to 100. The voltage across the secondary coil, or the voltage across the secondary, is equal to 10 volts. And the current through the secondary coil is 0.1 amps. We are asked to determine the primary voltage, the secondary voltage, the primary current, the secondary current, the number of turns in the primary, number of turns in the secondary, the power that flows through the primary coil, and the power that flows through the secondary coil. This could be S sub P and S sub S, but we've got purely resistive loads here, so there won't be any Q's. So the solution for this simple ideal transformer is that we have a relationship between voltage and current in the primary and in the secondary, and that's called the turns ratio. Turns ratio is equal to the number of turns in the primary divided by the number of turns in the secondary. And we can relate that to voltage and current in the primary and secondary coils of the transformer. Those relationships are Vp over Vs, the voltage in the primary divided by the voltage in the secondary, is equal to the turns ratio. And if we look at current, the current in the primary divided by the current in the secondary is equal to the inverse of the turns ratio. So between those three formulas, we can determine everything we need to in this problem. Let me scroll down so we can just see those right there. Okay, so if we want to solve this, the first thing we're going to do is to determine, in this problem, we can see that we're given NP over NS. So the turns ratio is just going to be 10 over 1. We would say this is a 10 to 1 transformer. You can write that as 10 if you like. So that means we know the ratio of Vp to Vs. Vp over Vs is going to be equal to 10. And so that tells us that Vs is equal to Vp divided by 10. And we take Vp, which is 12 volts, divided by 10, 10 there, and you get 1.2 volts is equal to the secondary voltage. So this 10 volts in, this 12 volts in goes down to 1.2 volts out. So this is a step down type transformer. The output voltage is lower than the input voltage. So we've got that. We weren't, in this problem statement, we weren't given any information about current, so we're going to have to solve the current in the secondary first by using the resistance. Ohm's law applies to transformers just like it does to any other device, and so IS in the secondary is going to be equal to the voltage across that resistor, which is just Vs, divided by the resistance itself. So that's going to be that 1.2 volts that we just calculated divided by 120 ohms. So that gives us a secondary current of 0.01 amps in that secondary. Now we can use the turns ratio to determine the primary current. We know that IP over IS is equal to NS over NP, which means that the primary current is equal to the secondary current times the inverse of the turns ratio. So that's going to be 0.01. And the turns ratio was 10 to 1, so the inverse is 1 to 10. So we've got 0.01 divided by 10 equals 0.001 amps. So that gives us our primary current right there. Now we can calculate the power in both sides. It's purely resistive circuit, so the power in the primary is the voltage in the primary times the current in the primary. That's 12 volts times 0.001. amps, and so that gives me 12 milliwatts of power consumed in the circuit. And in the secondary side, that's just the voltage in the secondary times the current in the secondary. So that's going to be that 1.2 volts times 0.01 amps. That also gives me 12 milliwatts. So we see that power is conserved in an ideal transformer. So in part B, we were not given the turns ratio, but we do have some other information that we can determine the turns ratio from, and that's the fact that we know the primary and the secondary currents. So we've got the ratio of IP to IS is going to be equal to NS over NP. I have these two quantities. I do not have, or I have these two quantities and I have NS. I don't have NP. So I can solve for NP. Is going to be NS times IS over IP. So the number of turns in the primary is going to be equal to the number of turns in the secondary, which we see up here is 100. Then we need to multiply that by IS over IP, which is 0.1 divided by 0.01. So that's 100 times 0.1 divided by 0.01, and we get 1,000 turns in the primary side. So we've got the is equal to NP there. So that tells us, if we wanted to write it, that the ratio of NP to NS is 1,000 divided by 100. That's okay to write it like that. More commonly, we would say that's a 10 to 1 transformer. So same ratio as in part A. So it's also a step-down transformer. We can, now that we know IP and NS, and we've got the turns ratio, we could go back and we can look at the other givens. We know the voltage in the secondary so that we can determine voltage in the primary. We haven't calculated R in the secondary yet though, so maybe we'll do that next. The resistance in the secondary is going to be the voltage in the secondary divided by the current in the secondary, so that was 10 volts divided by the secondary current, 0.1 amps, so that's 100 ohms of resistance in the secondary. And then we can determine the voltage in the primary. It's going to be equal to, well, the ratio is VP over Vs equals NP over Ns, so that tells us that we just take the voltage in the secondary and multiply it by the turns ratio to get the voltage in the primary. So we get a 10 to 1 times that secondary voltage, which was 10 volts. So we get 100 volts in the primary side of that transformer. Again, to demonstrate that the power is conserved, the power in the primary is going to be equal to primary current times primary voltage. So that is 0.01 amps times, let's see, 100 volts. So that's 1 watt. And power in the secondary is going to be equal to the secondary voltage, which was 10, times the secondary current, which was 0.1. So it's also equal to 1 watt. So again, power is conserved in the ideal transformer.